Hello students, today we'll continue our discussion on DC generator. So uh, in our last time class, when we discussed about the introductory section of DC machine, we have seen a generator is a machine that converts mechanical energy into electrical energy by using the principle of magnetic induction. So generators can be AC or they can be DC, like what we have seen in our last time class. If the generator is generating or producing an alternating current, we call it is a AC generator, and if it is producing a direct current, we call it is a DC generator. So whatever may be the type of the generator, all the generators, they convert mechanical energy into electrical energy, and their difference is an AC generator is generating alternating power and the DC generator is producing direct power, and both of these generators they produce electric power. The electric power is either AC or DC based on the types of generator, but they use the same fundamental principle called Faraday's law of electromagnetic induction. What is that Faraday's law of electromagnetic induction says? When a conductor moves in a magnetic field, it cuts magnetic line of force due to which an EMF is induced in the conductor. That is what Faraday says. So both AC and DC generator, they all operate with this principle of magnetic induction. We'll come to it later on a little bit in depth. So when we discuss about the constructional part of a DC machine, we said that our generator can have two main parts, the stationary and the movable part, we say. So the movable part, we call it an armature, and the stationary part, we say that it is the stator or the field winding. So when the DC voltage is applied to the field winding of a DC generator, a current flows through the winding and set up steady magnetic field. By Faraday's law, it means when we place the stator, when we supply the current to the field winding of this DC generator, obviously that current produces a magnetic field. This field, which is called field excitation, we call it an excitation. This excitation voltage can be produced by the generator itself, or it can be applied from outer sources like a battery. If the generator supplies its own field winding by itself, we call such type of a DC generator, it is self-excited type of generator, we name it. It is self-excited type of generator. Why we call it self? Because it is supplying its own field winding by producing its own DC supply. How this is happen? By using residual magnet. What does it mean? For example, a self-excited type is possible only if the field pole or the pole of that machine is permanent magnet. If the machine has a permanent magnet, there is a flux, it means. If there is a flux, and if we are able to move the prime mover or apply rotation, and if you have a conductor on the field winding, so by Faraday's principle, it is possible to induce the voltage, it means. So with the help of permanent magnet, the generator can produce its own voltage and supply to this field winding, so that it is supplying its own field winding, and such type of generator called self-excited type of generator. As you know, the field pole of a DC generator is stationary, and the armature conductor rotates always. So it means that it is a rotating part. So the voltage generated in armature conductor is of alternating nature. It means it's an alternating nature. We'll see this how it becomes alternating. And the voltage on DC generator, that alternatively generated voltage inside DC generator will be converted into DC by the help of commutator, as we have seen on the introductory part. So, in a generator, the prime mover or the mechanical force which is supposed to be input to the generator is going to be supplied through the prime mover, and the prime mover can be steam turbine, it can be diesel engine, even it can be electric motor. So we can apply this external mechanical force, then we produce the by applying external mechanical force, we are able to move the conductor inside the magnetic field so that the generator can induce the required voltage as per Faraday's law of principle. And the induced voltage depends on these four things. As you may remember, in our last time class, we have seen the magnitude of induced voltage. We said that E induced, now in this case what we can say generated voltage in a generator, it's going to be BLV sine theta, we say. So if you see this equation, it tells you the parameters which decide the magnitude of the voltage induced in the generator. What is this? This is a flux, and is the length of the conductor, and is the velocity at which the conductor is moving, and this angle theta, we say that it is an angle between the conductor and the magnetic flux, between these two. So the magnitude of induced voltage is going to depend on these four parameters. What are those parameters? It depends on strength of magnetic field, it depends on angle at which the conductor cuts the magnetic field, and the speed at which the conductor is moving, the velocity we mean, and the length of the conductor L. These are the factors which determine the magnitude of the induced voltage in our generator. And the polarity of this voltage depends on the direction of the magnetic line of flux and the direction of the movement of the conductor. Obviously, when the direction of the magnetic line of flux changes, the polarity will be changed. And when the direction of the movement of the conductor changes, the polarity of induced voltage is going to be changed. And the next point is construction of DC machine. Under this, I'm not going to tell you something new because we already addressed at the general perspective of DC machines. If you remember, we said that theoretically there is no physical difference between DC generator and the DC motors. And we call this collectively, they are called DC machines, we say. So, these basic constructional details are also valid for both DC generator and DC motor. And the constructional aspect of DC machines, what we have discussed before, it holds for DC generator, so nothing new point here. So all the component, the constructional aspect of the DC machine holds for DC generator. And let us come to the working principle a little bit in depth. So all the generators, they work on the principle of dynamically induced EMF, or by Faraday's electromagnetic induction principle. We said this before. What is laws are, just in order to express it in some other way, Faraday's law is going to be, some reference may get such definition. E induced is going to be d phi by dt. Induced voltage, it depends on number of conductor times rate of change of flux. This is what we call induced von Faraday's law. So change in flux, this d phi by dt, which we mean this one, change in flux associated with the conductor can exist only when there exists a relative motion between conductor and the flux. It means there should be relative motion between the conductor and the flux. Practically, either the conductor can be moving and fixing the flux, or the flux can be changing and fixing the conductor, or both can change at the same time. So we call a relative motion between. Therefore, this relative motion can be achieved by rotating conductor with a reference to flux, or by rotating flux with reference to conductor in order to get this relative motion. So the voltage gets generated in a conductor as long as there exists a relative motion between these two components. We mean conductor and the flux by Faraday's law. If there is a relative motion between these two, voltage is going to get induced. Such an induced EMF, which is due to the physical movement of coil with reference to flux, or movement of flux with reference to coil, we call it as dynamically induced EMF. We call this a dynamically induced. Why we named it dynamical? Because this voltage is induced with the reference with the relative motion or movement of conductor reference to flux, or flux with reference to coil. So according to Faraday's law of electromagnetic induction, whenever a conductor cuts magnetic flux, dynamically induced EMF is produced in it. That is a law. So we can say induced voltage in our generator, that we mean that it is a dynamically induced EMF with the law of Faraday's electromagnetic induction. So as you see from the diagram, if you have a magnet north and the south having a magnetic flux emerging from north to south, and if we place a conductor inside this magnetic field and make either the conductor or the flux or both to move relative to each other, definitely, as Faraday is investigated, there is an induction inside this coil or conductor. We call this induced voltage. The generated action requires the following components. There should be a conductor, like I said now. There should be a flux, and it requires relative motion between the conductor and the flux. If this parameter fulfilled, voltage will be induced in the coil. Now, in our practical generator, conductors are made to rotate to cut the magnetic flux, keeping the flux stationary. So, in our physical motor or practical motor, conductors are the movable part, or they are rotating and cutting the stationary flux. To have a large voltage output, a number of conductors are connected together in a specific manner to form winding, what we call it armature winding. Now, in this case, we are assuming just a single conductor. If we want to have large number of output voltage, we have to have large number of conductor, what it says here. In order to have large voltage output, we need to have a number of conductors arranged in a different fashion. either in a wave or lap winding manner of their armature. So the conductors are supposed to be arranged in a different fashion. We call that conductors armature winding. And the magnetic field is produced by an external source, what we call excitation, with the help of field winding. So the field winding produces a magnetic flux, and the conductors are already there, the armature windings, and we apply a force externally so that the voltage can be induced from such an arrangement by Faraday's law of principle. So the conductor placed on the armature are rotated with the help of some external device called the prime mover. The prime mover will apply this external force. So, like we mentioned last time, the magnitude generated will be, it depends on these four parameters: flux, length, velocity, and of course sine theta will be there, which is the maximum voltage. This is telling us it is at 90 degree, where sine theta will be 1. So this is the maximum induced voltage. The maximum induced voltage. And the direction of the induced current in a DC generator can be observed through Fleming's hand rule. Now, we already came to know that the voltage will be induced inside the coil by Faraday's law. But what is the direction of the current produced or induced inside the coil? That is determined by Fleming's right-hand rule. Fleming is the name of a person who investigated this for the first time. So what he investigated, what this rule says, that if we arrange our thumbs, foreign fingers and the middle finger of our right hand perpendicular to each other like this, perpendicular to each other 90 degree, of like this. I don't know whether it is visible to you. And if they are arranged in a 90 degree to each other, so he says that the thumb points towards the direction of the motion of the conductor. Thumb, this one, our thumb is going to indicate us the direction of the motion of the conductor relative to the magnetic field, and the foreign finger points towards the direction of foreign finger, this one, I don't know how can this one, foreign finger shows the direction of the magnetic field, and the middle fingers points towards the direction of the induced current, he said. It's like here. So our thumb indicates the direction of the motion or the velocity, and our forefinger indicate the direction of the flux, and the middle fingers indicate the direction of EMF or produced voltage. So here, as you see, if you put our right hand in this direction, so if the direction of our foreign finger indicate direction of flux, like it's emerging from north to south, so if we place this in this direction, and if our thumb indicate the direction of the motion, so if it means for my side, in my point of view, this is north to south direction of the flux, and this is direction of the motion. Obviously the induced voltage will point towards me, towards me. So that is how it is working. So the direction will be determined by Fleming's right-hand rule. And the magnitude of the induced voltage, obviously it is going to be BLV sine theta. BLV sine theta. And let me just tell you a little bit in depth how this is working. We call elementary generator principle. Consider a single turning coil rotating about its own axis in magnetic field, single coil, and two ends of the coil are connected in split ring commutator. See, this is the single coil or wire. This is a magnet, north to south, and we have brushes. This is a commutator connected to the end of the coils. So we have two commutator because two coils, I mean two end points we have, and we have brushes, and we are rotating this in the armature, I mean the shaft in this direction, and we have put a galvanometer which used to measure very small magnitude of voltage. If you connect like this and see how it works. For example, now in this case, sorry friend, the conductor is placed at 90 degrees to the flux. Assume that the flux is running from north to south, this side, and observe being at the shaft side. If we be at this side and observe the leg side, this coil is going to be point like this, right? Like this. So field is moving from north to south, and our conductor is placed at 90 degree to the field, 90 degree to the field. So when the loop of the wire is parallel to the magnetic line of flux, now in this case, don't forget that we are observing from the shaft side, so that's why it is the loop becomes a dot. So when you see the physical placement of this loop, it is in parallel to the magnetic field. It's parallel to the magnetic field. So in this case, there is no cutting of flux. Cutting of flux. We mean that no cutting action is taken place in this case. Since the line of the flux are not being cut by the loop, it is directly placed in parallel. No EMF is induced in the conductor, and the meter will not read any values. So the meter at this position indicates 0. This point we call it is a neutral plane axis. It's a neutral plane. It is where zero flux, I mean zero voltage is induced. Now a little bit, let us turn 90 degree to this. When I rotate 90 degree clockwise, now see the black side now become, it was down now, it was down now. When I rotate in 90 degree, now it become in the southern pole. Southern pole, the black one. So when the shaft turns 90 degree clockwise, the conductor cuts through more and more line of flux, because the whole part of our loop or conductor will get cut by the magnetic flux. That is the maximum possible where our loop can produce maximum induced voltage. So this voltage induced in the conductor is going to be maximum. At the continual end, the induced increase and angle EMF in the conductor build up from 0 to the maximum value. It means when we turn from 0 degree to 90 degree, we will not do it instantaneously. Obviously, we'll slowly shift from 0 degree to 90 degree, and at that time the voltage is also increasing from 0 to maximum voltage. Again, let us turn 90 degree further. Let us turn 90 degree further. Now we mean that with respect to the beginning one is going to be 180 degree. So at that time, so the loop has completed 180 degree of rotation and is again parallel to the magnetic flux, which is the same as this one, but in the opposite direction. As a loop turned, the voltage decreases until it reaches 0. Now, it was maximum in this case, and we keep on rotating again another 90 degree, and 180 degree from the 0 degree. Now to produce a maximum field. Minimum field is going to be cut this conductor, but in opposite direction. So it starts reducing, the induced voltage start reducing. Again, further 90 degree, it will become to similar with the 90 degree of this one, but opposite direction. So in the opposite direction, the maximum flux is going to be generated. The maximum the maximum voltage is going to be induced in this case. Maximum voltage. So now note here, when the conductor moves from 0 degree to 180 degree, now the conductor is existing in the same pole. Now in this case, the black was under south pole, and in this case also it is all south pole, so the direction is not going to be changed, the same. After 90 degree, now the black side is going to be turned to the north side. At that time, the direction of this current is going to be changed. See, in this case it was like this. Now when it is in north side, it is going to be shifted or reversed.